Hi, I'm Professor Seth Chandler from the University of Houston Law Center, and this essay is on classification and discrimination. It's part 4, the last, in a series on the topic. It's for the course Analytic Methods for Lawyers, and it builds on the understanding of classifiers and discrimination developed in the prior 3 videos to examine a very real-world use of them, helping to make decisions about whether a prisoner should be released or not. The use of machine learning to make this sort of decision, both in theory and in implementation, has been highly controversial. The respected investigative body, Pro Publica, has charged that the algorithms discriminate against minorities. The creator of the COMPAS algorithm, Northpointe, has vigorously denied the charge. This essay confirms that the algorithms behave in a discriminatory manner, as charged by Pro Publica, but that Northpointe's defense of that behavior has considerable force. Virtually all of the discrimination involved arises from the higher incidence of observed parole breaking among African Americans, and very little of it from the algorithm itself. Northpointe is no more guilty of invidious discrimination, and no less, than most of those developing machine learning models to work on groups with different incidences. The behavior noted by Pro Publica is generally math, not racism. The essay does suggest, however, that the costs of inaccuracy, which are particularly severe in this area, could be reduced by preserving use of a strong classifier, but not insisting on the same thresholds for labeling a prisoner as likely to break parole or observe it. We'll also discuss how, with some modest increase in the costs of inaccuracy, one could achieve greater levels of equality in the treatment across races. Let's talk about the controversy. So the controversy motivating this essay arose in 2016 when Pro Publica charged that the COMPAS machine learning system developed by Northpointe was committing errors that worked to the disadvantage of minorities. The organization performed a number of statistical tests that it said ruled out various benign causes for the discrepancy. Here's the photo that got the article started, and here's the headline. Machine bias, there's software used across the country to predict future criminals, and it's biased against blacks. Now, Northpointe responded vigorously to the claims made by Pro Publica. It alleged there were various technical errors in the group's work. More fundamentally, however, Northpointe said Pro Publica's work did not properly take account of the differential recidivism rates of the racial groups, and noted that its measure exhibited accuracy equity. It was as accurate on African Americans as whites, and the AUC score, which we've talked about in this course, was about the same on all groups. What Northpointe's response did not address, however, were any fundamental reasons, independent of accuracy, why classification with different incidents is likely to lead to the sort of discrimination its own study or its own system was alleged to have generated. Nor would I say did the Northpointe exposition really do full justice to the strength of its statistical arguments, and that's a factor that I think may have contributed to the ongoing criticism of that organization, but here's at least the title page of the Northpointe response. Well, we weren't done. Pro Publica fires back with a defense of its original report against the Northpointe brief, saying that it stood by its conclusions and findings. And although it didn't use the term calibration in its response, the actual meaning of Pro Publica's rejoinder was, I think, that Northpointe's system wasn't calibrated properly. Among those who were given a certain score from Northpointe, whites recidivated at a higher rate than did blacks, the implication being that blacks therefore deserved a lower score. There's been a lot of scholarly work done on the COMPAS data itself and on the problems that it's noted. It's almost become an academic subfield. There's a Kaggle data set, and there's a lot of papers that look at COMPAS and its machine learning system. I think actually the most noteworthy of these works comes out of a group led by Morris Hart, now a professor at Berkeley, and formerly with Google Research and Google Brain. And this essay and the 3 that precede it actually make a lot of use of the ideas that were developed in that work. I should say that Pro Publica has acknowledged this work and its conclusion that certain forms of discrimination in machine learning may be mathematically inevitable. And here's a copy of the front part of the paper, Equality of Opportunity in Supervised Learning, that really motivated me to start looking into this field. Now, others have noted the point developed here that the type of problem raised by the Northpointe machine learning system is in some sense nothing special. This could be good or bad, depending on your perspective, but I think abstracting the problem away from a particular context is often useful. Professor Gelman, a professor of statistics and political science at Columbia, has made this point. This is a situation where even if the system could be calibrated correctly, meaning it's equally accurate between racial groups, it can be unfair to different groups, Gelman said. From the perspective of the sentencer, it might be unbiased, but from the perspective of a criminal defendant, it could be biased. Efforts in the field have been fostered by various researchers making the data public in various formats and with various forms of cleaning applied. I'm going to rely on the work of Matthias Bernstein, who argued in a way that I found quite persuasive that the Pro Publica research made some poor choices when it came to figuring out the relevant length of time in which to observe released prisoners to see if they recidivated. And so I'm going to adopt his decision on which data points to include or exclude. It doesn't actually make a huge difference, I think, in the actual outcome, but I think he's correct and you might as well do it the right way. A programming note. There's just no way to make the programming for this essay simple. I've really done the best I can, and I've worked very hard to use functions previously used in this series of essays and in this course, but I have to rely on functions created and for this essay and on previously unseen resource functions. So please just realize that this isn't simple material. I won't pretend otherwise, and I've tried to make it as lucid as possible. Okay, let's start computing. I'm going to start by retrieving the data. Here's where I got it originally, but it's sitting on my hard drive and I'm going to import it. And as we suck it into my computer, it's going to have 7,214 rows, each of which has 53 columns of information. This is the code to do the import. I'm going to import it as a data set, which will make it format nicely. All right, and there we go. 7,214 rows. We can see more on it. A lot of this stuff we don't need, in my opinion, like I don't really need to know about Courtney Coleman or when Courtney's birthday is. I just need to know some of the other data in here, like what age Courtney was at the relevant time, how many priors Courtney had, etc. Okay? A number of cleaning measures I've done. I've done some date filtering to take account of the Bernstein notion. I've renamed some columns in a fashion that makes it easier to work with in Wolfram language. As I said, I've eliminated columns that I'm not going to use. And I end up with a data set at the end of the day called Florida 3 that's going to be the basis for the remaining work. And let me actually restart my kernel, so I'm starting with a nice clean kernel, and then we'll resume. All right, let's start with a nice sparkling kernel. I'm just re-importing that data set. Here what I'm doing is I'm only going to take data where the screening date was before April 1st, 2014. That's the Bernstein idea of dealing with a problem in the data. I'm going to eliminate certain characters in the variable names. Wolfram does not like underscores. By the way, this takes a little bit of time here to do the stuff with the date. Date arithmetic is not one of the speedier features in Wolfram language. I'm going to then, once this is done, I'm going to only take certain columns. We're going to take the sex, age, race, juvenile felonies, juvenile misdemeanors, juvenile others, priors, whether what they were charged with was a felony or misdemeanor, and whether within a 2-year period they recidivated. So let's get that activated, and I really do think, there we go, hold on. Okay, I want to work not with recidivism as being a 1, I want law-abiding to be a 1. So we're just going to fiddle with that here. and rename the variable to be abide rather than 2-year recid. There aren't really enough Asians and others and Native Americans to really do much statistical analysis on them, and so I'm going to sadly lump them together, which I know is really not the best thing because they're not the same thing, but there are limitations of the data. All right, and now I've got my various cleaning operations. Let's actually run those cleaning operations on the data, and then I'm going to turn it into a data set where I only show 5 rows at a time. And we will assign the data set to be called Florida 3. So there's our cleaned up data set. You'll notice that the date screening got us down to 6,216 rows, which is going to be enough for us to work with. All right, I've explained the meaning of the various columns, and what we're trying to do is to predict whether they're going to abide by the law during that 2-year window. And I should say that we don't really know whether they abided by the law or violated the terms of the parole. This is a rather important point. We just know whether they were determined to have done so, and that could be the result of a disproportionate enforcement against certain racial groups. It could be the result of a criminal justice system that has bias in it. So this is not a measure of ultimate law abidingness. This is a measure basically as to whether they escaped detection, which probably has some relationship to whether they abided by the law, but not a perfect one. All right, let's get some descriptive statistics on the data. First of all, who are we talking about here? We have 3,139 African Americans in our data set, 2,132 Caucasians, 563 Hispanics, and 382 others. We can also see what the behavior looked like among each of the racial groups, and we can see that, I'm sorry, this is just we haven't gotten to that yet. We can look at these as fractions. So our African Americans are about 50% of the population, Caucasians 34%, Hispanics 9%, and that other amalgam 6%. Now here's what I want to look at. I want to look at the correlation between race and whether they abided by the law, with that footnote that abide doesn't really mean abide. And what we can see is that every group does abide. It's just that the ratios are different. Like in the Hispanic group, there's well more than 2 to 1. So too with Caucasians and others, but in the African American group, while there are definitely a majority that abide, there's a significant minority that are said not to. So we can look at this on a percentage basis, and we can see that the abide fraction, which is really the incidence of the positive class, because we're going to call abide our positive class, differs across racial groups, not hugely, but it does differ. And you'll also note that we're in a setting in which African Americans are both lower incidence and lower entropy because it's closer to 50%. And based on our work in the previous videos, particularly video number 3, we should sense that this story could turn out poorly for African Americans as a result, because classifiers are going to struggle disproportionately on groupings that have higher initial entropy. All right, we can also just look at this column here, and we'll see this is just the incidence by race. Okay, so as I said, given these stats, I know based on what I've seen that this is going to be an uphill battle for African Americans to get justice from the classifier. But you don't know until you look. So let's see what turns out. All right, let's seed our good old random number generator, and we're going to split up the data as we always do, or almost always, into training and testing. I want to scramble it, so if there is any order in that data set, I've now gotten rid of it, and we'll have 4,351 rows in our training data, and the remaining, whatever it is, 1,700 or so as test data. All right, now we're going to do what you should now be an expert at, which is building a classifier using Wolfram language, seeing how it performs on the test data, and then we'll get some properties out of the test data. So let's run this. I'm going to use gradient boosted trees. It's got a real good track record, and some scouting work here indicates that it's a good choice. So I've turned training progress reporting off so we don't have to see it, and it'll run a lot faster. And by the time I say boo, it is almost done. There we go. All right. Now let's develop a classifier measurements object for the entire test data set. And I do that. And let's take a look what we got here. So it's generating 70% accuracy, although the baseline's 64%, so it's not doing wonders. What you can see is that there are a number of false positives here. It's having a hard time figuring out who's not going to recidivate. It's doing really quite well among those who will abide, but it is struggling with those who, in fact, will not abide. So, not terrible, not great. All right, and if we want to get some stats, I'm going to use this resource function property association. This is, at the moment I'm recording this, an unofficial resource function. That's why it's not orange there. But I hope that by the time you view this, or in a few weeks, that this has become an official resource function. So I want to get the accuracy. I want to get what the receiver operating curve, characteristic curve looks like, assuming 1, which is abide, is the positive class. What's the area under the curve for that positive class? And then for those who recall the Cohen-Kappa statistic, that's a measure of how well the classifier is doing relative to a random classifier. And so what we see is it's going to have to go and find the property association resource function. It's now, I hope, done that. And there we go. All right. So again, 69.97% accurate. Here's our ROC curve. Remember, we like that ROC curve to kind of be up there. We certainly don't want it on that line. That's the random classifier line. The area under the curve's 0.71, meh. And the Cohen-Kappa statistics, 0.29, meh. As I said, this is not a terrible classifier, but it's not a great classifier either. And it may well be, remember, this is my classifier, not Northpointe's. Northpointe's classifier, they spent more than 2 minutes, I certainly hope, developing it. They had access to a little more complex data, but there's nothing between what I'm doing and what they did that's going to really change the qualitative conclusions here. All right. Let's see how the classifier performs by race. To do this, I'm going to use our friendly MapReduce operator. This is going to group the data by race and do nothing to it. And then for each group, we're going to create a classifier measurements object by running the classifier against that group, determine their probabilities for each person in the group, compare that to the targets, and we'll use the test data for all of this. So we're going to develop classifier measurements for each race. It's a dot here, and that's because it's just sort of too big to fit in that data set. But if I were to click on this, for example, you can see that inside there is indeed a classifier measurements object that's going to tell us how the classifier is performing on that particular group. But let's get a survey of the results. And to do that, we're first going to use property association. That's one of these unofficial resource functions that I've written to try and get some data out, including the confusion matrix. This messy blob of code is designed to use the confusion matrix to get 2 things out that it's a little hard to do otherwise. One is the incidence of the positive class. The other is the positive rate, the fraction of people who the classifier says are going to abide. And once that's done, I can drop the confusion matrix. This stuff is just to make it pretty. So let's run that. And let's take a look at these results. So we can see that the false positive rate and true positive rate for Caucasians are higher than for every other group. and they're particularly higher than they are with respect to African Americans. False positive rate is significantly lower. True positive rate is also lower. And so you can see right there, Pro Publica had a point. There is a difference. And you can see why people could be concerned about this. It somehow does not really seem right that if you are not going, if you're going to abide by the law, that only 77% of those people will be classified as positive if they're African American, whereas 93% will be so classified if they're Caucasian. And similarly, it might be grading if among those who are in fact not going to abide, 80% of those will be mistakenly classified as abide if they're Caucasian, but only 51% if they're African American. You can also see, though, Northpointe's point that the classifier isn't that much different in its accuracy among the racial groups. Yes, it's a little lower for African Americans than, for example, Hispanics or Caucasians. On the other hand, the area under the curve for African Americans is higher than it is, it's actually significantly higher than it is for Caucasians. And so this is not, I should say, Northpointe's classifier. This is my classifier. But its classifier basically, as far as I can figure out, exhibited the same characteristics. So a point for them from Northpointe there. But this discrimination exists. Finally, let's look at another issue that Pro Publica spent some time on in that response to Northpointe's response to its initial article, which is look at the difference between the positive rate, the probability of being classified as positive, abiding, versus the actual probability of abiding. And for Caucasians, they get like an 18, 19 point bump here, percentage point bump. And others get like a 17, 18 point bump. So the classifier is kind of being kind to them. Among Hispanics and African Americans, yes, the classifier is being kind, positive rates higher than incidence, but not nearly as kind. And so you can again see the basis for saying that the classifier is unfair in its treatment of people across races. Well, remember in essay number 3, we looked at three-dimensional ROC curves. And so let's look at the three-dimensional ROC curves here and see what's going on. And the first thing I'm going to do is I'm going to build a little data set in which we've got the false positive rate, the true positive rate, and then I also want all the points on the ROC curve. And to do this, I'm going to rely on another unofficial resource function, one that I hope will be made official shortly. It's one that I wrote, but it's going to extract those ROC points from deep inside the classifier measurement object where they are squirreled away. All right, and we get a little data set telling us that there are 650 points for Caucasians and 916 for African Americans, etc. And we can now use that structure to do some graphics magic here. I don't think you need to understand this code. That's one of the reasons I've iconized a lot of it away. What you should admire, however, is the beautiful picture that it produces, which is showing these three-dimensional ROC curves, and there's a color-coded point on each of them for exactly where the classifier has determined the best spot to be. We can view these three-dimensional curves from different perspectives, and I think it's actually useful to do so. So that's what this manipulate does here. And here we're looking down. We're looking at it from above. And so this is the same thing if I did something like that to my original graphic, but it's a lot cleaner to do it programmatically, and that's what I've done here. So you can see the relationship between the false positive rate and the true positive rate for all the groups, and you can actually see that Caucasians are kind of lower for a good chunk of it than are, for example, others, and you can see that African Americans and Hispanics are kind of straddling each other. This is one of the reasons, though, you might think, well, this means that the classifier is tougher on whites, and this is why you kind of need a three-dimensional classifier to get the full picture, but this is a conventional presentation, and it is actually quite useful. Here's a look at the relationship between the false positive rate and the threshold. We can get a look at the relationship between the true positive rate and the threshold, and then here, if you want it, you can go back to your default view. Time for a new concept, the convex hull. Now, we actually kind of had the idea of the convex hull when we were looking at equal odds in previous videos, and I was showing you how you could get to the interior of the ROC curve, but now we're going to make really heavy use of it. What I want to do is to look again at this three-dimensional ROC curve, but look at it from above. And what you'll see is that it is not invariably convex. And what I mean is, you see how I could go from here to here, or from here to here, or from on the blue curve from here to here, and all of those points would appear to be forbidden to me, right? I've told you you're not really supposed to go up and to the left of the ROC curve. But if you think about it, remember what we learned, which is that if you pick two thresholds, you can get anywhere in between them just by saying, we can get 40% of the way between here and here by saying 40% of the time we'll apply this threshold and 60% of the time we'll apply this threshold. And so really these points here are attainable if you're just willing to permit some random thresholding to be used. And so what we can draw is sometimes called the convex hull of all the points generating the ROC curve, and that represents all of the points that are actually attainable. So let's first of all get those points. I'm going to illustrate it for Hispanics, not for any particular reason, just because it seemed like a reasonable thing to do. So there are our three-dimensional ROC points for Hispanics. It's 177 by 3. All right. At the moment, although we can generate three-dimensional hulls, and we definitely will generate three-dimensional hulls, it's a little easier to see in 2 dimensions. So I'm just going to take the first 2 points, the false positive rate and the true positive rate, for each of the points along the three-dimensional ROC curve. Right? Now we have a matrix that's 177 by 2. Now let's generate their convex hull. And thankfully there is a Wolfram language function that generates the convex hull, and it's called convex hull mesh. It's called mesh because it's going to generate something called a boundary mesh region that we can visualize. It's like a graphics primitive that we can visualize. So I'm going to say, get me the convex hull mesh created by the 2-dimensional Hispanic points, and then we'll just do a little decorating here, and then I'm going to also show you the ROC curve. These are the points themselves, and this is the convex hull of the points. All right, so what you see is that it's exactly what I said, like you can get in between the points now. Like this point right here is within the convex hull, even though it's outside, strictly speaking, of the ROC curve. So that is, I think, a beautiful illustration of the convex hull. There is functionality, you should know, to test whether something is inside the convex hull. You just say region member, here's the region, and then we'll test these points, and it's going to turn out that 0.2, 0.6 is outside the convex hull, whereas 0.2, 0.46 is inside the convex hull. We can also think, as I mentioned, about a convex hull in 3 dimensions. And these are the combinations of false positive rate, true positive rate, and threshold we can obtain so long as we're willing to flip results, as discussed in one of the prior videos. So the coding here is thankfully simple. It's just our command convex hull mesh. These are our three-dimensional points. This is just to color the resulting region blue, make it translucent, and there's some other aesthetic glop there. All right, and there it is. You can look at it from different angles, and that's our convex hull. And again, we could test whether a point's inside the convex hull, and it turns out that this one isn't, and this one is, and this one isn't. All right, so what does this all mean? What it means is that the optimization problems we're about to perform are much easier than they would be if we did not have a convex region to consider. And maybe that's too mathy a point, but as someone who struggled for quite some time to get the minimization and the algorithms all working here, the realization that this was actually a problem of convex optimization made my heart at least go pity-pat. All right, let's talk about the costs of inequality, what happens when we impose different constraints on the recidivism classifier. And here, what I'm going to do is, just like we did in the prior video, we're going to look at an unconstrained solution where there are no special constraints on the classifier. We're going to require it to have demographic parity, that is an equal positive rate among the various racial groups. We're going to look at equal opportunity, having an equal true positive rate among the four groups, equal odds, requiring both an equal false positive rate and an equal true positive rate among the racial groups, and equal threshold, which says simply that whatever threshold you're using for all the groups has to be the same. And my goal is going to be, as it was in the prior essay, to minimize inaccuracy costs subject to these constraints, and then see what statistics we have, like the false positive rate, the true positive rate, the positive rate, the accuracy, the inaccuracy costs, the threshold, etc. I'd be lying if I told you this was the easiest programming in the course, but thanks to the convex optimization, it's not quite as dreadful as it might be. First thing we're going to do is we're going to develop a function that computes inaccuracy costs, and basically, if you think about it, what we need is the false positive rate and the false negative rate. But we don't generally get the false negative rate, but it's super easy to compute. It's just 1 minus the true positive rate. And then, if you think about it, what are the inaccuracy costs? Well, let's look at the false positives. We have a rate. How many of them are there? Well, it's 1 minus the incidence. And what's the cost? The cost is the ratio of false positive costs to false negative costs, which are going to be assumed to be 1. The false negative costs are going to be assumed to be 1. And then we should add to that the cost of the false negatives, and that's the false negative rate times the number of people who are positive. So that's the incidence, and so that's our formula. Okay? The rest of this code is just to get data that's not in this nice form into that nice form. So what if we have an association with the data? And then what we have here is the total inaccuracy costs not only depend on these things like incidence and cost ratio, but they depend on how many people are in the class. Like if there are 947 people in the class, in that racial group, I'm sorry, then the costs of inaccuracy are perhaps more important in that group than if there were just 3 people in a racial group. So we need to multiply, when dealing with weighted inaccuracy, we need to multiply our regular inaccuracy costs by their prevalence. And so let's make sure Mr. Wolfram knows about that. And so we're going to end up with an inaccuracy costs function that's a function of 3 clusters of parameters that are not related to the choices as to false positive rates and true positive rates. And then we'll add in these parameters relating to false positive rates and true positive rates. So what is all this stuff? This is the fraction of the population. That's each of the ethnic racial groups. These are the African Americans for A, C is for Caucasians, H is for Hispanics, O is for others. These are the cost ratios among those four groups, and this is the incidence of the positive class among those four groups. And the idea is we're not able to really change this. That's sort of outside the scope of our exercise to change what fraction of the population in prison is Caucasian. And similarly, we're not able in this exercise to change what the incidence is. We're not able to run reform or education programs that would change the incidence of abidingness or recidivism among the four racial groups. And then this is just the data set that we need to make this function work. And let's actually look at an example of it. Here are the imagined percentages of the fractions of the population of each racial group. Here are the cost ratios, and here are the different incidences among the four racial groups. And so that's going to generate a function. Okay, this is a function particular to this scenario, but it's a function of the false positive rate among African Americans. Don't worry about the dollar sign, it's just sort of automatically thrown in there. This is the false positive rate among Caucasians, blah, blah, blah. And here's the formula. And now we can take this function, which I've called ICF, and we'll now give it the 8 arguments. Here's the false positive rate among African Americans, here's the false positive rate among Caucasians, blah, 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 and here is the true positive rate among others, okay? So we do that, and it comes out with a number. That's the cost of inaccuracy. So we could actually now build our own objective function that corresponds with the data that we actually have. Here's the fractions of each racial groups. We actually computed that before. It's just in a different form. Here are the cost ratios. I'm going to assume the cost of a false positive is the same as a false negative. If you want to change that, that's great. You have all the code you need to do it. I would encourage you to play around. And then here's the incidence of abidingness for each racial or ethnic group. And that's going to let us produce our objective function, which is just the inaccuracy cost function with these parameters now slotted in. So let's fix that typing error. And there we go. There's our function. Now, the numbers aren't all that important right now. What is important is that if you look at this, it's a linear function. There are no fancy cross terms, no quadratics, no square roots. It's just multiply the false positive rate of African Americans by this number and multiply the true positive rate of Hispanics by this number and add it all up. And that fact, coupled with the convexity of the region in which the variables are permitted to range, that convex hull business, is what's going to make this optimization way, way easier than it would otherwise be. And you'll be happy to know the hard work's done. It's like analytic methods is like painting. It's all in the prep. So what we now want to do is minimize inaccuracy costs subject to bounds constraints and ROC constraints. We're going to minimize it for the 8 variables, the 4 false positive rates, and the 4 true positive rates. And this is all the code we need. It's not much. Here, we're going to compute our convex hulls. Here's the hull for African Americans. Here's the hull for Caucasians, Hispanics, others. So let's generate those. And you see, instantaneously. And now, let's compute. Here's our objective function. Here are the things we get to play with. False positive rate for African Americans, all the true positive rates. And here's our constraints. The false positive rate for African Americans, the true positive rate for African Americans, and the threshold for African Americans has to be inside their hull. Same thing for Caucasians, inside the Caucasian hull. Same thing for Hispanics, inside the Hispanic hull. Same thing for others, inside the other hull. And the idea here is we're saying, look, if your false positive rate is 0.1, you don't get to have a true positive rate of 0.9. That's not permissible. The classifier just isn't that good. So, and then so these are our objectives, these are the constraints, and this is what we're trying to solve for. So here we go. We're done. Less than 1/10 of a second. And we find out that the minimal cost of inaccuracy is 0.2949 blah blah. And here are all of the various statistics, the various rates that result in that optimization. We're going to come back to what the meaning of it is, but for now, let's just get the computations under our belt. For demographic parity, we need the true positive rate to be the same. I'm sorry, the positive rate, not the true positive rate. We need the positive rate to be the same. We're going to need a little bit of code to generate that constraint. We're going to need to know the incidences so that we know how to weight the false positive rate and the true positive rate. But the code here is exactly the same. The only thing we're going to add is this demographic parity constraint, right? And that's a function of the incidences I. We're done. Those are the values, and you can see that the costs are a little higher with demographic parity. Let's do equal opportunity. Equal opportunity, it's the same as the first optimization problem. Everybody's got to be in their hole, but the true positive rate for all the groups has to be the same. We're done. Equal odds. And you realize this is like the whole paper, or the whole essay. It's just that we've done so much prep work that now the code just executes in no time. Same deal with equal odds. The true positive rate has to be the same, just like with equal opportunity. But now also the false positive rates have to be the same. And there we go. Final piece of code is equal threshold. Equal threshold, same objective function, same stay in your holes. And then the constraint is that the thresholds have to be the same. The African American threshold is the same as the Caucasian threshold, is the same as the Hispanic threshold, is the same as the other threshold. And we're done again. All right. Let's actually turn that into something that we can visualize. So here's some code that's going to build a nice data set that we can look at, and I'm going to move it over, so move this out so you can see the whole thing, and good, it just fits. One other thing I think will be useful to see at the outset before I go into a detailed analysis is another way of visualizing this data. Here it is. Through some effort, I have produced a beautiful graphic in which we put those convex hulls color-coded, and we have where does the various regimes end up placing the various racial groups. So here's what happens if things are unconstrained, and you can see the low true positive rate among African Americans, for example, the high both false positive and true positive rates among Hispanics, and you can compare that to what would happen if we had equal opportunity, where the true positive rate is the same for everybody, or equal odds, where you can't even see the different points because they're right over each other, or demographic parity, or what the equal threshold would look like. So I encourage you to play around with that. It's just another way of trying to visualize the data that's up here. And let's look at that data. So let me take what I think is the most important finding first, which is, look at the costs of inaccuracy. Yes, they are higher for equal odds and demographic parity, but not really very much higher. This is less than 5% higher. And so, for a small cost, a small extra cost, you can get a system that has a good deal more equity. You don't have to give up on your classifiers. You can use the same classifier. You just set different thresholds than you did in the unconstrained model, and the result is greater equity. Now, we can talk about whether that's fair, and we can also push back a little bit perhaps on the notion that, well, only a 4 or 5% increase in costs. But let's tell the following story. Supposing we moved, let's say, from an unconstrained regime to one of equal opportunity. And so the in order to implement that, the threshold for African Americans dropped from 55% required to 43% required. Well, suppose there was an African American who had a 49% score. Under the unconstrained regime, they would not have been let out, whereas under the 43% regime, they would. And of course, some of those will be mistakes, and you could imagine the Willie Horton horror story when one of those people is released after imposition of an equal opportunity justice regime, and that person goes out and kills somebody. So if you're the victim or their family, you're not going to think that, oh, going from 0.295 to 0.305 was just a little thing. You're going to think it was a cataclysmic and grievous error. Or, similarly, imagine you're a Hispanic who, under the unconstrained regime, you had a 45, and so that was enough, 45%, that was enough to get you free, and you might very well abide if you were let loose. But now, in order to achieve the glorious equal opportunity, the threshold's been raised to 0.485, and your 0.45 score no longer qualifies, and so you're stuck languishing in prison, which also, you're not going to think that's a small deal, even though the increase overall was rather small. So, while it is definitely true that the increases on a percentage basis are small here, if the costs of error here are large in an absolute sense, then even small percentage increases can be something to be concerned about. Second finding is the Pro Publica results are right staring us in the face. You can look at, for example, the false positive rate among African Americans in the unconstrained or its cousin, the equal threshold regime, and you'll see that they are much lower than for other ethnic groups, and the same thing for the true positive rates, okay? Much lower for African Americans here and here than for the other ethnic groups here and here. And so you might well think that's unfair if you're unlikely to commit a crime, then whether you're released or not really shouldn't depend on your race. And so you could see how this would be quite troubling. What else do we see? Well, we see, as I mentioned, the thresholds adjusting in order to take account, in order to basically make the constraints come true. You can see what one might term affirmative action in demographic parity, where look at those differences and even differences with other ethnic groups, equal opportunity or equal odds. We can also see, by the way, that our glorious N minimize worked, always something to be comforted about. In equal opportunity, for example, we see that the true positive rates are in fact all equal. In equal odds, we see that both the false positive rates are all equal and the true positive rates are all equal. And we see in equal threshold that the threshold is all the same. So that is comforting that it all worked. So I think those are the major conclusions from the work so far. Again, I just want to reiterate what we showed earlier, which is this gap between positive rate and incidence, and using that as a basis for saying that the unconstrained system is indeed unfair. That's something that Pro Publica talked about a fair amount, and indeed you can see that concern being reflected in the data here. Okay, one last thing before we wrap up a four-part series, and that is this really machine learning's fault? This discrimination that we're seeing, is that really the consequence of these fancy machine learning algorithms? So let's just see. I'm going to run something that we could have run 50, 60 years ago, logistic regression. We certainly could have done this 30 years ago. We had enough computational power. Might have had to use, well, probably not punch cards, but it was doable. Here's the code. We're just going to take our training data, run it through logistic regression, wait a few moments. It's done. Now let's get a classifier measurements by race. This is the same code. The only thing that's different is that it's based on logistic regression rather than those nice gradient boosted trees I used before. And now let's get out our stats. And what do we see? Well, we see exactly what we saw basically with the fancy gradient boosted trees. False positive rate for African Americans, true positive rate for African Americans, lower than for the other groups, accuracy lower than for the other groups. So this is evidence again that it's not machine learning that's responsible. It's just that we're focusing on it more that now that we have machine learning. The problem would have existed if you'd used logistic regression 50 years ago, and in fact, arguably the problem's worse because the accuracy rates are lower, which is disturbing in and of itself. Well, maybe that's logistic regression. Maybe if we used a different technique, we'd get something different. So I'm going to try using a shallow decision tree, which I'm going to implement as I have before through a random forest, and it's a very sad forest. It only has one tree, and it has very big leaves to prevent any coarse, fancy decision trees from existing. I've built my decision tree. Let's get how it performs on the different racial groups, and let's visualize it. And it's the same picture. The false positive rate and the true positive rate for African Americans lower than for other groups. Accuracy, yet lower still, so higher inaccuracy costs. And again, this is just the result of what we saw in the preceding videos, that when you have a situation of low entropy, because the incidence is kind of in the middle, and lower incidence than you do in other ethnic groups, the classifier is really going to struggle, and it's likely to treat you disadvantageously unless you do some fiddling with the threshold rates. Also, let me draw just one other point here, which is one could think, based on this, that the abidingness of African Americans is actually lower than other racial groups. That's not necessarily the case, because we don't know whether they really abided the same. We just know whether they got caught. And if you spend more resources trying to catch people based on race, or the justice system is biased against people based on race, then you're going to end up with a perceived higher rate of recidivism, which is then going to compound the problem, because now you're going to have African Americans being classified as likely to recidivate, not because they actually do to any greater extent, but just because they get caught more frequently. All right, so we started off with the controversy and who won. Well, I think Northpointe, I'm going to acquit them of having deliberately concocted some sort of aggressively racist classifier using a Frankenstein machine learning technology. Really, as I've said repeatedly, the problem is low incidence, high entropy, and that the problem's going to occur if you use state-of-the-art machine learning, less advanced statistical algorithms, or I am willing to bet human rules of thumb that respond to the data, because the bad guy here is math, and Pro Publica's great discovery of math does not make those employing it evil. On the other hand, depending on what you mean by discrimination, any of reasonable classifier, including the one developed by Northpointe, including the one developed by me, results in African Americans being treated in somewhat of an unfair way, and Pro Publica was right to expose that. And what this essay shows, I think, is actually the discrimination can be fixed here without incurring a particularly large marginal cost. And so if I were to be asked what's the chief contribution of this work, I would say it's to develop a framework for thinking about the costs of equality. And while there may be little to do for now about whatever factors are driving African Americans to, quote, recidivate, close quote, more frequently than other groups in this data set, and we can, however, maybe prevent compounding that disproportionate reincarceration with a refusal to release individuals. And so if it's not too costly, I think we ought to consider use of different thresholds here in order to create greater equality in results across races. And that brings us to the end of an epic. This has been a 4-part series on classification and discrimination. I hope you've learned a lot about, if nothing else, receiver operating characteristic curves, convex holes, various metrics of classification success. That's from a programming sort of math standpoint. From a legal standpoint or ethical standpoint, we are going to see the issues that I've discussed here arise all the time as machine learning comes to the forefront. And even though it's not really machine learning that's causing the problem, it is machine learning that is going to potentially be blamed for the adverse results that we can now see. So I hope that these essays give you, and videos give you, a critical framework for thinking about the issues in the years to come. Thank you very much.